So frequently, like gamma is taken to be beta. So what I am going to do is that like I am going to give you a homework problem. Okay, so where you essentially draw the Nyquist plot and bode plot of this particular transfer function, okay, sinusoidal transfer function, and then like comment. So let's say we choose the following values. We choose Kc to be 1, gamma to be 10, beta also to be 10, and let's say T1 to be 1 and T2 to be 10. Okay, so let's say we choose T2 and T1 in this fashion, right? Okay. So what we are doing is that like I am choosing 1 by T1 and 1 by T2 to be 1 decade away, right? So that's what I am doing, right? And then like the lead compensator will essentially have a slope as far as the magnitude curve is concerned 1 decade from 1 by T1, and similarly the lag compensator will have a what to say frequency range of interest 1 decade below 1 by T2. Okay, so that's how we just split them as 3 equal components. Okay, I'll give you the answer, you just solve it, right? So let's say like you essentially choose these values, right? So what you need to do is then plot the Nyquist plot and the bode plot of C of j omega. Okay, so that's your homework. So I am just going to draw the Nyquist plot, sorry, not the Nyquist plot, the bode plot, the log magnitude curve to be more exact, so that like we will visualize how this is going to look like, right? So let me draw the magnitude of C of j omega, of course in decibels. Okay, so what are the critical frequencies? We are going to have 0.01. Okay, we will have so since 1 by beta T2 will be 0.01, that's why I am taking from 0.01, right? 1 by T2 will be 0.1. Okay, then I have 1, then I have 10, right? So these are the 4 frequencies, right? So what I am doing is that I am just calculating the values of 1 by T1, gamma by T1, 1 by beta T2 and 1 by T2, right? That's what I have marked for this particular example. So what is 0.01 for this particular example? How do you get 0.01? This is nothing but 1 by beta T2, right? 0.1 is essentially 1 by T2. This is 1 by T1. This is gamma by T1. I hope now it's clear how I got these 4 values. Okay, these are the 4 frequencies, and the way we have chosen these numbers, we have ensured that the gaps in the logarithmic scale are the same. Okay, that's just done by convention. No, that's it. Okay, so let's look at what happens to the. I am just going to give you the answer and then discuss. So what will happen in this particular case is that the asymptotic plot, obviously it will start from 0, okay, and then it will reduce to -20, then stay at -20, and then it will go back to 0. Okay, so this is what happens with this, with the log magnitude curve of this particular transfer function, the lag lead transfer function. Okay. Right. So you can immediately see that the lag part kicks in first, right? In the lag lead compensator, the lag part kicks in first, right? Because you can immediately correlate it to whatever we learned, right? The lag compensator's log magnitude plot is going to have a structure like this, right? So it's going to stay constant, decrease, and then stay constant, right. So that's what you are going to have in the first part due to the lag part, and then the lead part kicks in, and then the magnitude value increases and then becomes constant. Okay, so that is the structure for this lag lead compensator, right? Yes, please.
The lag is kicking because we've chosen T1, T2.
Yeah, depends on the value chosen, exactly, right. So if you look at it, you know, like what is the what can you say about the nature of this particular compensator? What does it do? It takes an intermediate frequency range, right, and then attenuates that frequency range alone, right. So that's the structure which is taken by this lag lead compensator, right. So you can immediately see that that's what is going to happen, right. So please plot the what to say, Nyquist plot and also the phase plot, okay, corresponding to this particular transfer function, okay, and just make observations as before, right. And that's something which I am going to leave it to you as an exercise or a homework. Is it clear? Okay. Fine. Okay. So this completes our what to say, discussion as far as the theory part for this course on control systems is concerned. So what I am going to do is that, like I am just going to summarize whatever we learnt in this course, so that like we get the big picture viewpoint, right. So and then you can also help me in summarizing what we really learnt in this in these what to say lectures, and how we will use them, right. So let's do that. So let's summarize all the topics that we learned, right. So where did we start, if you recall? Sorry? Stability, you know, like see, think about from the first class, right. Okay, so I'm just what to say, essentially giving us bullet points, right. So we first started with what is a system, right, what is a dynamic system, correct. So and then like what are the classes of dynamic systems based on whether it's linear or non-linear, what is the definition of time invariance, causality, and so on, right, single input, single output systems, okay, and all those classifications were first learned, right. So that's something which we looked at, okay. Then what did we do? Laplace transforms, okay. Before that, properties of what? Systems. Of course, yeah. So we looked at the classification. We also identified the class of systems that we are going to study, right. So now everything whatever we learned, you know, as far as this particular course is concerned, you know, like is applied to what class of systems? Yeah. Yeah. So if you recall, we identify the class of systems to be studied as linear time invariant, causal, single input, single output, dynamic systems, right. So that's the class of systems that we have analyzed, okay, throughout this particular course, right. So then what did we did, you know, like we looked at characterization of dynamic systems using mathematical models, right. So that's what we learned next, right, how one can use essentially models to characterize. And then we also learned what is the typical class of models that we will use. If you remember, you know, like lump parameter or spatially homogeneous, dynamic, continuous time, right, deterministic models, right, that's the class of models we essentially used. So ultimately what we figured out is that like this essentially comes in the form of ordinary differential equations, right. So consequently what we did, you know, like we essentially revised a few important mathematical tools, particularly related to complex variables and Laplace transform. Okay, we learned how Laplace transform can be used to solve ODEs, right? And since for this particular class of systems we will get linear ODEs with constant coefficients, there is only one solution, which is the exponential function, right? So that's why exponential functions are pretty important. Okay, then what did we learn? Sorry? Yeah, of course, by Laplace transform I refer to all its properties, examples that we did and so on, right? So then we looked at, of course, we also did one more thing, right? So of course, in this is not in the same order, but then we learned how to essentially represent the model, which is given in terms of ODEs in two representations, right? The transfer function representation and the state space representation. Of course, throughout this course we looked mainly at the transfer function representation, although we had a brief discussion on what is the state space representation, how can it be obtained, and what is the equivalence between the two, right? That's something which we discussed. But we took the transfer function representation, then what did we do? We learned about poles, zeros, right? And then we also use the Laplace transform to look at free response, right? Forced response, and we learned that the transfer function is typically used to characterize the forced response, right? Free response is essentially removed because the initial conditions are taken to be 0. But is that a viable approach? You know, like, because in reality we are always going to we may have a non-zero initial condition, right? But then by now you would have realized that if we design stable systems, the coefficients that come in the solution that depend on the initial conditions will be multiplied by exponential functions with a decaying or with a negative exponent. So what really happens is that if you consider the free response of a stable system, that anyway decays to 0, and what persists, the steady state value and also the steady state response and even the transients to a large extent would be influenced by the forced response, by the input that we get, right? The free response would affect the input if the initial conditions are non-zero, but the argument which is typically given is that, like, look, anyway the contribution of the free response is anyway going to go to 0, right, if you design a stable system. That's why we are looking at the forced response predominantly, right? Then what did we learn? We learned two important topics, right? That of stability and performance, right? So we learned the definition of Bibo's stability. And of course, by stability, you know, like, then we added an adjective there. We learned something called relative stability. So people call this as absolute stability, right? So we learned what is called as Bibo's stability, what is the notion, and then, like, we learned stability criteria. We figured out that for Bibo's stability, a necessary and sufficient condition was for all the poles to lie in the left of complex plane, right? And then, like, we learned the route stability criteria to figure out, you know, like, how one could evaluate whether a given system is stable or not, or conversely, how could one design controllers to ensure closed loop stability, right? So that's something we learned, correct? Then we also looked at performance. How did we quantify performance? If you recall, we looked at first order systems, right? Second order systems, and then, like, looked at you know, like, various parameters like time constant, rise time, peak time, overshoot, and so on, right? Settling time. Okay, so all those parameters were used to essentially quantify performance, correct? So then we looked at predominantly PID controllers, right? So we learned the structures. What is the structure of the PID controller? What was the contribution of each part, proportional, integral, and derivative? What are the pros and cons of each component in the PID control? what to say, control structure, and essentially we did a few examples, right, and we learned, you know, like when we got an intuitive feel of when to use what, right, because when we have poles at the origin or poles on the imaginary axis for the plan, what to do, and when we have poles in the right of plane, which controller would suffice and so on, right. So those things we figured out by doing a few examples. Then if you recall, we studied about the root locus, right. So root locus essentially was used to plot the locus of the closed loop poles, and then this was used for control design, correct. So if I'm given the open loop transfer function, if I vary one parameter, which may be a controller parameter, how do the locus of the closed loop pole change, you know, like, and that was used to essentially design the closed loop system for stability and performance, right. So after this we moved to frequency response. Yeah, okay, fine, that's right, you know, like, so where would I put it? Let me put it under performance, okay, because anyway, thank you. So I think I missed out writing steady state error analysis, right. We learned various definitions of various parameters, Kp, Kv, Ke, and so on, right, and when to use what, and we looked at different types of system, type 0, type 1, type 2, and so on, right, and what is the implication of those systems. We looked at frequency response, then we learned what it was, and then how it can be visualized using bode plot, Nyquist plot, right. So and then we learned the Nyquist stability criteria and so on. Okay, so that was another thing, and finally what we did was that, like, we essentially looked at relative stability, right. We looked at various parameters that can be used for quantifying performance in the frequency domain, like gain margin, phase margin, and so on, right. Then we looked at cutoff frequency, bandwidth, and so on, right. So that's something which we did, and finally, of course, we looked at lead, lag, and lag lead compensation, right. So that is another just choice of controller transfer functions that you have, right, depending on the type of system that you have, you choose either. And I hope that this course essentially also serves as a starting point, right. If you want to essentially learn advanced control theory, you know, like this, whatever we learnt in this particular course would be the fundamentals based on which you would build, right. So that's the expectation of this particular course, okay. So if you go back and look at what were the learning outcomes of the course, you know, that we discussed in the very first class, you know, like essentially that's been listed under the summary, right. So we have learned what is called as classical control theory, right, for a particular group of systems, fine. So that's about it as far as the theory is concerned. So I thank you for your attention.